binary, take this binary and put it in the center of a dense star cluster, then the binary will undergo interactions with other stars and black holes in the star cluster. And for example, one black hole can replace and kick off the light star. What's so funny, Selma?
Yeah, I love this. We're dealing with this kind of Feynman diagrams.
Oh, I never thought about that. That's nice. If the black hole kicks off the light stars and forms a new binary, then this gives birth to a binary black hole. And black holes are particularly efficient in acquiring companions through these exchanges because they are usually more massive than the other stars in a star cluster. And dynamical exchanges favor the formation of more and more massive binaries, which are more energetically stable. So this sounds like a good reason to investigate and quantify these effects in star clusters. To do so, we have to do something that is a computational challenge, because we should account for embody and count as actually direct embody. We need a direct embody code because we need to solve Newton equation directly, which is quite expensive. And we need stellar evolution and binary evolution because a star does not stop evolving just because it is in a star cluster. It still evolves and transfers mass to companions. So what we did is we put together direct embody simulations with embody 6++ GPU and stellar and binary evolutions through our population synthesis code. And we're still running a very large set of simulations of young star clusters. This is actually the largest set of simulation of young star clusters that has been run to study binary black holes with initial conditions that mimic the clumpiness of young star clusters and with the highest binary fraction that has been considered, 40%. Initial binaries are the bottleneck of this calculation. And this work has been led by Ugo Di Carlo, a PhD student in my group, and Sara Rastello, who's a postdoctoral fellow. So from these kind of simulations, we can gather a lot of information about binary black holes. I will have time only to mention masses. So this plot again shows the distribution of the total mass of black holes that merge within a Hubble time. But here is for the dynamical simulation. In particular, the blue histogram shows the masses of binary black holes that form from exchanges. In orange, the masses of black holes that evolve in star cluster, but they come from original binaries, so binaries that were already in the initial conditions and evolved in the star cluster. And the gray histogram is a comparison sample and shows a set of isolated binaries that was evolved with the same stellar evolution and binary evolution as the star cluster binary. So dynamics with exchange, dynamics without exchange, no dynamics. And we see quite clearly that exchange binary black holes are significantly more massive than the other. We can even form binaries, merging binaries with a mass of the single black hole higher than 60 solar masses, and they can merge thanks to dynamics. But even the original binary black holes, those that evolve in star cluster, have masses that are significantly larger than the gray sample because dynamics tend to suppress the merger of the lighter black hole binaries. And finally, here, among those very massive systems, a fraction of them has a primary black hole in the peri-instability mass gap. So about 2% of these merging binaries host a black hole with a mass in the peri-instability mass gap. And these are not second-generation black holes like the one that Carl recently studied. These are black holes that form from multiple mergers of very massive stars and can avoid peri-instability. I can give you more details later if you're interested. So I will give you my take-home message about formation channels, which is it is really computationally expensive to study the formation of binary black holes, especially with dynamics. But luckily, the features of dynamical evolution are quite different from the feature of isolated binary evolution. So with dynamics, we expect more massive binaries. We expect even black holes with mass in the gap, in the peri-instability mass gap. And dynamics can affect also other quantities like spins, eccentricity, and the merger rate. And I will give you more details in the discussion if you are interested. But now, in the very few minutes that I have left, I would like at least to mention the importance of cosmology. So, LIGO and Virgo are not going to observe mergers at higher redshift. They will observe merging binary black holes up to redshift 1. But if a binary black hole merges at redshift 1, it means that it may have formed at much higher redshift. So if we want to give a sound astrophysical interpretation of what LIGO and Virgo observe, we need to study the evolution of these systems. Plus, we are now considering the science cases for the next generation gravitational wave detectors, and they will be able to probe binary black hole mergers up to redshift 10 or more if there are black holes merging at redshift higher than 10. Then it's definitely important to study the cosmic evolution of compact objects, but it's also a computational challenge because of the humongous physical range that is involved. In our group, we are currently following this strategy, Monte Carlo-based strategy, to do this, which is from population synthesis and dynamical simulations. We get information on the masses and the delay time of merging system. Then what we need from cosmology is essentially the star formation rate density and the metallicity evolution in the universe. We get this either from cosmological simulations or a data-driven approach, like Madal plots. We put things together with a Monte Carlo approach, and we can predict the cosmic merger rate and the properties of the host galaxies by considering a large parameter space. I will have time to give you just one example because there were many questions, so I think I will stop here. And the example is the reconstruction of the merger rate density of binary black holes as a function of look-back time or redshift in the comoving frame. All these color lines here show different population synthesis models where we change kicks, core collapse supernovae, common envelope prescriptions, while we kept the same star formation rate, the same metallicity evolution. The star formation rate, which comes from the illustrious cosmological simulation, is shown by this gray line. There are basically two things that we are happy about this plot. The first one is that all of these color lines approximately match the behavior of the star formation rate density. So star formation rate density is definitely important ingredient here, but in some cases with a small shift to higher redshift. The peak of star formation rate is about redshift about 2.5, while the peak of binary black hole merger rate is about 3. This is basically an effect of metallicity. And then the second thing is the normalization of the curve, which changes wildly depending on the population synthesis prescription that we use. And this is very good because LIGO and Virgo are going to reduce the uncertainty on the local merger rate density very soon. So we may be able, in some future, to constrain the binary evolution processes with this kind of approach. Yeah.
Is this driven by electricity and distribution, the plot that you show here?
The plot that I show here comes from population synthesis simulation for the formation of binary black holes and cosmological evolution. With the cosmological simulation.
Yeah, that's exactly my point. So, as far as I know, Illustris doesn't have enough resolution to restore black holes that tiny that it's actually interesting for LIGO. So when you're using, a order of like about 100 solar mass or less.
Yeah, we put a black hole inside. So basically, we have star particle from the illustris. We know when these star particles form and what is its metallicity. Each star particle is like 1 million solar masses. Then we assume that this is just a stellar population with 1 million or so stars inside. And we add a stellar population simulated with population synthesis to this stellar particle, and some of these stars and binaries will become binary black holes. What I'm more worried about, the last risk, is the fact that it does not get completely right, the star formation rate, the metallicity, and this is what we checked by checking what happens if you change the resolution, but what happens if you override the metallicity evolution with some other prescription. And we also went for models that are data-driven. So let's take the star formation rate density from the Maddow plots and the metallicity evolution from observations. I mean, none of them, neither the cosmological simulation nor the observations are good enough to tell this is actually the evolution. But if we can kind of compare our results, we can quantify the uncertainties and make sure that we understand things and with a given uncertainty.
But in principle, you can just, like what you said, you can just leave it observational evidence, observational constraint on metallicity and Maddow, you know, form.
Yeah,
like
this is what
for a star formation. You don't really need to put it in less stress.
it depends on what you want to do. So here, with the data-driven approach, we have the advantage that we can run many more models because it's more computationally fast. But for example, metallicity evolution is not very good up to high redshift. So we get this sample from the Chia and collaborators which study a dampened Lyman alpha systems up to redshift 5, but we know that they cannot get completely right the normalization. So they are good at measuring the gradient in metallicity, but not really the normalization. So